Okay, today's lesson is 7-1 out of our textbook. It is exploring exponential models. Now, I did start off in class today. I asked the question for you to think about which one you would prefer. If I were to give you 1 penny a day, that's supposed to be a penny a day for 30 days, so every day of the month, and I would double it each day, or would you rather have $1 million? That's $1 million right there. So a penny a day, doubling it each day. So the first day you would get 1 penny. The second day you would get 2 pennies. The next day you would get 4 pennies. And then 8 pennies. So forth and so on. So you're doubling the number of pennies that you get each day. Which would you rather have? Get that penny, or would you rather have $1 million? So if you want to know the answer to that, you can do the calculations or come see me and I'll tell you. Or email me. Okay, so that's what leads into our exponential discussion. So remember from the past, repeated addition can be represented with, in the example we talked about, if you have 5 plus 5, okay, don't do that to me. Put that back. Put that back. All right, 5 plus 5 plus 5 can be written as, most of y'all knew, multiplication. So 5 plus 5 plus 5 is the same thing as 5 times 3, because I have 3 5s. That's repeated addition. Repeated multiplication, 5 times 5 times 5, we would use what to write that? And you knew that that was exponents. So we use exponents to write repeated multiplication. Now, so first off, what we're going to be able to do and what we're going to talk about is to define what an exponential function is, and then we're going to talk about graphing them. So an exponential function is a function in the general form of y equals bx. So this is what we've referred to before as the parent function. Okay, this is your parent function, and you'll be asked that question as we go through and are learning. Okay, y equals b to the x, and b has to be greater than 0, and it cannot be equal to 1. And that's not what I wrote. B cannot be equal to 1. Okay? All right, so look at the graph, because one of the things that we've been working on all year is being able to look at a particular equation and know the general shape of the graph, and then we used key points to actually plot them. Okay, so excuse me, to do that, start off with, we would have b greater than 1. And if b is greater than 1, then your function is going to look something like this. Okay, and this point right here, as they point out, is your y-intercept, and your y-intercept is when x is 0. So b to the 0, anything to the 0 power is 1. So they knew that the y-intercept was going to be 1. So if b was greater than 1, then my function was going to be increasing. If b is less than 1, but always greater than 0, then my function will be decreasing. And again, when you put 0 in, you're still going to have 1. So this is why our key points are -1, 0, and 1. We're going to figure out what's happening on both sides of that y-intercept. -1, 0, and 1. And then if you put 1 in right here, you have b to the first power, which is b. And you're going to see how we're going to use this in just a second. So -1, 0, b, starting at the bottom, b, 1, and then 1 over b. Because b to the -1 means I'm going to put it in that bottom and make it positive. Okay, so let's go see. Oh, actually, we're going to answer a few questions about that. So, domain and range. Domain, what number is farthest to the left here? -infinity. What value is farthest to the right? Is positive infinity. Okay, also could be known as all real numbers. You could say it that way. The range, all right, the lowest value that we have is 0. It is not equal to 0, so it's parentheses. The highest value going on forever and ever is infinity, never equal to infinity. Okay, what intercepts do we have? It crosses only the y-axis at 1, so we have 0, 1. And then we have this thing called an asymptote, and I'm not sure how many of y'all remember this from Algebra 1, so I'm going to just remind you that an asymptote is a line that a curve approaches but never touches it. So if you look at my graphs, okay, each of these, you should be able to see that it's getting closer and closer to the x-axis in both of these cases, but it actually never ever touches it. So I'm going to highlight it, whether you want to highlight it or draw it thicker with your pencil. I will always ask you to actually graph that, because I think that graphing the asymptote is going to help you tremendously. So whether you highlight it, the equation is y equals 0. So you can highlight it or write it right next to it if it happens to be one of your axes. If it's not an axis, then I'm going to expect you to plot it. Okay, so let's go do some of our plotting, graphing, however you want to call it. All right, so what is the graph of each function? So the first thing that you're going to do when you're graphing functions is you got to determine what is your b. What is the base of that function when we're thinking of y equals b to the x? So b is 4 in this case. It's the base of your exponent. So if b is 4, then my key points, -1, 0, 1. b is 4. That's always 1. And this is 1/4. Because we just flip that number, whatever it is. That's why you're going to find out it's much easier to always have them in fractions. And my asymptote, as we said, is y equals 0. So I like to start off plotting my asymptote, or drawing my asymptote, however you want to think about it. So I'm going to draw that, and now I'm going to come back and plot my points. So I have -1, 1/4, and we're just estimating, y'all. 0 is at 1. And 1 is 4. Now, before I continue that, I'm going to go back and tell you that one of the things that I talked about back up here that I should have mentioned. When we were talking about the fact that this is repeated addition is multiplication, and repeated multiplication is with exponents. One way I think it helps you remember is if I took, so if I took an equation, okay, y equals 5 times x, that is what the graph of it looks like, which we've spent a lot of time doing. That is a line, and since it's a line, it's called a linear function. Well, if I change that and said, let's don't make it 5 times x, let's make it 5 raised to the x, and when I graph it, you will see what it's looked like, which is what we just talked about, okay? So it's a curve, it's no longer a line, but more importantly, I wanted to talk to you about the table of values. So if you hit Control-T when you're on the Inspire graphing calculator, here is your table of values, and you can see that when it is 5 times x, I'm adding 5 every time. So a linear function, and we talked about this when we did our problems, a linear function, that means that there's the same difference between each of these numbers. I'm adding 5 as I go this way, or I'm subtracting 5 if you go that way. If it is an exponential function, I'm not adding 5, I'm actually multiplying by 5. And you can think of it as multiplying by 5, or if you're going the other way, then you are dividing by 5 each time. But more importantly, that is how you can look at a table of values and know whether or not you have a linear function or an exponential function. In a linear function, you will be adding or subtracting the same number every time. If it's exponential, you will be multiplying or dividing by the same number every time. Okay, so back to this. When I'm graphing this particular function, when you graph it, again, I didn't know if I was on this point. So when you graph from this side, you always want to approach your asymptote. You don't want to cross it. And when you're coming from this way and you're going up, I'm asking you to not cross this line unless you know what that number is. That would be if I put 2 in there. Well, if I put 2, as we just talked about, if it's an exponential function, then I'm multiplying by the same number every time. And what that number is I'm multiplying is whatever that b value is. So times 4 times 4 times 4 makes this next number 16. So 216 is way up here off my graph. So when you graph it, make sure you don't draw the line to cross that, because it doesn't. It stops. It goes way up there, which is off our graph. Okay. We'll keep talking about that, so hopefully it'll make more sense as we go along. Okay, so look at this next one. Y equals 1/3 to the x. What is my b value? It is 1/3. Okay, so my table of values, again, -1, 0, 1. And then I'm starting with 1/3 at the bottom, working my way back up, 1, and then 3 over 1. And again, my asymptote is y equals 0. So I'm going to go, not the right one, I'm going to go here, and I'm going to draw my asymptote. And now I'm going to plot my points. So at -1, I have 3. At 0, I have 1. And at 1, I have 1/3. Now, again, pick that point that's medium up there, and I'm having trouble seeing, so I'm going to see what I can do. And draw it towards your asymptote. Okay, that was really bad. Sorry, it's harder to draw on this than on pencil and paper. Okay, go towards your asymptote, and then when you come the other way, think about what that next point with. If this is 3, my numbers, I'm dividing by 3 as I go this way, but I'm multiplying by 3 if I go this way. So that next number would be 9, when that would be -2, which is right here. So if you want to connect it, you can, but if not, just make sure you stop right there. So I'll take either one, like I said, but do your best to connect those points. Make it approach your asymptote, and then it shoots up pretty fast. That's what an exponential function is doing. Okay, let's look at this last one. What is b in this problem? And I will tell you that every single one of my classes today said b was 6. And b is not 6, because our order of operations says you got to do the exponent before you multiply. So, and more importantly, the base is of the exponential part is 3. So b is equal to 3, which gives my key points, -1, 0, 1, 3, 1, and 1/3, and asymptote is y equals 0. And from here, now the difference between this last one and these first two is I now have a value here. And we talked about what does that affect? Does it affect the x or the y? And if you can't remember what we talked about earlier in the year, we've talked about, we look at this and we say, is this inside or outside the parentheses? Is it affecting x or is it affecting y? And if it's outside the parentheses, it is affecting y. And I'll tell you, on the exponential function, y'all, if it affected the x, it would be up there in the exponent. Okay? So this is affecting the y, which means I'm going to take each of these y values and I'm going to multiply them by 2. So now I still have -1, 0, and 1. But I'm going to take 3 and multiply it by 2, 1 and multiply it by 2, and 1/3 and multiply it by 2. And I'm going to do the same thing to my asymptote. What is 0 times 2? 0. So my asymptote did not change in this particular problem. It is still at y equals 0. And let's go back and plot our points. So at -1, I'm at 2/3. At 0, I'm at 2. And at 1, I'm at 6. So the one that's, not getting smaller but going bigger, okay, the next one, just to test yourself, what would be the next point? Well, what is my b value? My b value is 3, so I'm multiplying that by 3. So if I were to go again, it would be 2, and then it would be 18. Okay, and I'm only doing that, y'all, for the numbers that are getting bigger, not the fraction ones. which again is clearly off our graph. So let's see if I can connect those. Come on. All right, but I missed. I'm going to try one more time. There we go. Okay, so in summary, and it's in your book this way, which is why I wanted to have it on here, so in case you look at your book, okay, to help remember. All right, here is what they're referring to as their exponential function. It's a little different because they have an a value, and that's fine, okay, but a is positive in both of these cases, and if a is positive and b is greater than 1, is my function going to be growth or decay? Well, we kind of talked about it up above. And if b is greater than 1, then we're going to have exponential growth. And if b is less than 1, but always greater than 0, we're going to have exponential decay. All right, and the last thing to talk about, well, in either case, the y-intercept is always 0a. It's kind of what we just saw in this case here. When you have a number in front, whatever that number is, that is where it's going to cross. These didn't have a number in front, so if they don't have a number in front, then it's going to cross at 1. Okay, so your y-intercept is going to be 0a. Domain is always all real numbers, and the asymptote is the x-axis, which has the equation of y equals 0. So we're going to fill that in, asymptote. So if you have your handout, you turn it over, and these are the kind of problems that we have to answer with this concepts. Okay, so this first one that we have here, identify each function or situation as an example of exponential growth or decay. What is the y-intercept? Okay, it is growth, and I'm going to ask why it's growth so that you can know. It is growth because b is equal to 4, because it's that base of your exponent, and 4 is larger than 1. All right, so that's why we have growth. What is your y-intercept? It's that number that's in front, so it is 0, 3. Okay, look at the next one. Is it growth or decay? Well, my b value here is 0.75, and 0.75, what does that, is less than 1, and less than 1 means I'm going to have decay. My y-intercept, again, the number out front, 0, 11. Okay, look at this next one. You put $2,000 into a college savings account for 4 years, and the account pays 6% interest annually. Well, I hope that you can figure out if it's paying you money, then that thing is growing. So it is growth. And the y-intercept is how much money you started with. You started with $2,000 because that 0 is representing time. Time is 0. And when time is 0, that's how much I have at the beginning when we're first starting out. So it's 2,000. Okay, so a very real-world application of this concept gives us lots of word problems. So we have something with exponential called exponential growth and decay formula right here. Keep in mind, we've talked about this. This is notation. Do not divide by a, do not divide by t, do not multiply a and t together. It is notation. A represents the amount after t time periods. Okay, so one of the things to remember about the formula, A is the initial amount. We've already talked about that. That's how much you start with. R is your rate of growth, and you have to, oh, pooh, how did that happen? Oh, I know what happened. Oh, well, sorry. Let's go back here to that. All right, R must be a decimal when you put it into this formula. Okay, so R is your rate of growth, and if it's positive, you have, if R is positive, it's growth. If R is negative, you have decay. So if you look back up at this problem that we did with the interest, okay, you might have been confused thinking 6% is doesn't seem If that's a decimal, that's 0.06, which is less than 1. You might have thought that was decay, but R itself is positive, so there's growth. The growth factor is what's in here, and that would be 1 plus R, which in this example would have been 1.06. And that, of course, is larger than 1, so it's still growth. Okay? Now, the other thing that you need to be aware of in this formula, you will have all different kinds of time periods. That means you could have minutes, you could have seconds, you could have hours, you could have days, you could have months, weeks. Okay, obviously there are many, many more, but just keep in mind that you're not limited to years. And we will be learning another formula later that it's always years in that formula. But this one, it can be any unit of time. So look at our problem. Suppose you invest $500 in a savings account that pays 3.5% annual interest. How much will be in the account after 5 years? Well, I, of course, like to start off by writing that formula because it helps me learn the formula. And then I look back and I like to read the question. And if it's asking me how much will be in the account, then that's telling me that I am looking for the amount after time t. So that means I know what all these other variables are for reading the problem. The initial amount, how much am I starting with? $500. 1 plus R. Where's my R? Well, there's my rate. R is standing for rate. But remember, I have to make that a decimal. Okay? And you change from a percent to decimal by either moving your decimal place over to the left 2 places, or put that in your calculator, 3.5 divided by 100, it'll give you that decimal. So 1 plus 0.035 raised to the t. How long am I going to keep it in there? 5 years. So put that in your calculator and you will get an answer of $593.84. So there you have it. Okay, one last problem. It says, suppose you invest $500 in a savings account that pays you 3.5% annual interest. When will the account contain $650? Okay, so this one's different. We got the same example that we had up top, but this time they're asking me when will it happen. That means I'm looking for t in that formula. So in my formula, a of t equals little a 1 plus r to the t. They want to know when is it going to be $650. And we could say equal to. We'll say equals. Keep it simple right now. Wait. Equals. How much did I start with? Still started with 500. 1 plus 0.035 to the t. Okay, stop it. Go away. Golly, got to be kidding. Oh, I'll see what happened. Okay, so hopefully I'm back. There we go. Okay, so how do you solve an equation when you have a variable in the exponent? You haven't learned it yet. So the only way that you know how to do this problem is to use a graphing calculator, or a lot of y'all have calculators that have a table feature on them, and if you know how to use the table feature. So I'm going to do it with the Inspire so that you can see, and we're going to go over here, and I am going to take the table off of there. I'm going to put a new page in, and I'm going to go graph what we just said, and that was 500 times 1 plus 0.035 raised to the, okay, y'all don't put a t. What are we graphing in? Okay, we're graphing in y and x, so you got to put an x when you put it on your calculator. Don't put a t. Okay, so then you hit enter, and you're like, holy cow, I can't see my graph. What did I do wrong? Okay, so this is why it's so important to know the intercepts of your graph. What is the x-intercept of that graph? If I hit tab, okay, we've talked about this. This is your exponential function, and that means that that right there is your y-intercept. So, go ahead and put that back. Put that back. Okay? And that means that I have to go up here. Oh, whoa. I just learned something new about my, anyway, I'm going to go tap that because that's what you can do. You can use your little, what do you call that thing? I can't remember now. Little, click pad, whatever. And you can go double click on that. And I say, I need to go above 500 because 500 is my y-intercept. My equation was actually asking me about 650. So I'm going to put it at 700. And there's my function. But that's the reason you weren't seeing it, because you're seeing just the small part of the graph around the origin, and that's not where it is because the y-intercept is at 500. Okay, but more importantly, on a table, okay, which you can do on a table feature or this one, Control T brings up my table, and the problem said, when will the account contain at least $650? So I'm looking at these numbers to see when will I have at least $650. And if you notice, it's right there at 8. So at year 8, you will have $658. So we're going to answer it and say, after 8 years, we will have at least $650. So yeah, it's actually before 8 years, but we're not finding out exactly. So that would be the easiest way to answer that question, using your table before we know how to solve it. All right, so that's the end of lesson 7-1. If you have any questions, please email me or come by and see me. Thank you so much.